All right, let's dive into one of the biggest, most fundamental ideas in all of calculus, the limit. Now, it might sound a little intimidating, but trust me, it's all built on a really cool idea. Sometimes, the journey is way more important than the destination. Let's see what that actually means.
So to get our heads around this, let's use a simple analogy. Picture this blue curve as a path, like a hiking trail. As we're walking along it, a limit is what tells us the exact height, or elevation, that we're getting closer and closer to as we near a specific spot on the ground.
Okay, Section 1, Approaching a Destination. Let's really dig into this idea of approaching. You know, it's something we all get intuitively, and it's the absolute heart of what a limit is all about.
And here's the kicker, the crucial distinction. When we talk about limits, we don't actually care about what's happening right at our final destination. A limit is more like a detective with a magnifying glass. It lets us inspect the behavior of the path right around that point. We're looking at the trend, the direction. You could almost say we're looking at the intention of the path.
Section 2, Decoding the Notation. Of course, mathematicians needed a super precise way to write all this stuff down. And yeah, it might look a little strange at first, but don't let it scare you. It's best to just think of it as a new language, a kind of shorthand for describing this whole idea of approaching a destination. Here it is in all its glory. And you'd read it out loud just like this. The limit of f of x as x approaches a. See? It's really just a sentence. So let's break down what each part of that sentence actually means.
First up, you see that lim. That's the limit operator. Think of it as the action word, the verb in our sentence. When you see this, it's giving you a command, an instruction. Hey you, find the destination value that this function is heading towards.
Next, we've got this little bit x with an arrow pointing to A. This is our GPS. It tells us where on the map we need to look. It's describing our movement along the x-axis, the ground beneath our path, as we get closer and closer to some specific location we're just calling A.
And then there's f of x. In our little story, this is the path itself. It's the actual winding road we're walking on. It's the rule that tells us our height, our y-coordinate, for any given spot x on the ground. And finally, the whole thing equals L. L is the answer. It's the prize we're looking for. L is the limit value, that one specific destination height that our path, f of x, is zeroing in on as we get infinitely close to A.
Section 3, the substitution shortcut. Okay, so we get the language, but how in the world do we actually find L? Well, the good news is, for a lot of functions, the ones that are well-behaved, with a nice, smooth, continuous path, there's a wonderfully simple shortcut.
And it all comes down to this. If our path is perfectly smooth, with no potholes, no gaps, no weird breaks, then the destination we're approaching is exactly the same as the spot we actually land on. In these easy-peasy cases, finding the limit is as simple as just plugging the number right in.
Let's try one out real quick. We want to find the limit of 3x squared plus x minus 1 as x approaches 1. Now this function makes a beautiful, smooth, unbroken path. So all we have to do is substitute 1 in for x. We get 3 times 1 squared plus 1 minus 1, which just equals 3. Boom, the limit is 3. Seems pretty straightforward, right? But it is absolutely not always this simple.
And this is where things get really, really interesting. This warning right here is the whole key to understanding the true power of limits. So what happens when the destination you're approaching isn't actually a place you can stand?
Section 4, A Hole in the Path. This brings us right to the core concept that makes limits so darn useful. What if there's a hole in our path? What if there's a single missing paving stone right where we expect to land?
Just take a look at this table of numbers. We're zeroing in on an x value of 3. Notice what happens from the left side. As we go from 2.9 to 2.99 to 2.999, our height, our f of x, is getting crazy close to 6. And what about from the other side? From 3.1 to 3.01, it's the same deal. The height is also getting crazy close to 6. Both sides of the path are pointing us to the exact same height.
And this slide says it all. This is the key difference. The actual value of the function right at x equals 3, it might not even exist. It's literally a hole in the graph. But the limit, the destination we are approaching from both sides, it absolutely exists. And it's 6.
So here it is, the main takeaway. A limit could not care less about what's happening at that one single point, A. All it cares about is the neighborhood around A. It's all about describing the journey and the intended destination, even if that destination itself has vanished into thin air. Section 5. Smooth versus broken functions. Okay, so why are we so obsessed with this hole in the path idea? Well, it's because this idea finally gives us the mathematical tool we need to define the difference between a smooth path and a broken one. And that brings us to continuity.
So here's the deal. A path is continuous at a point when the journey perfectly matches the destination. The limit, where you're headed, is exactly the same as the actual value of the function, where you land. The hole is filled in, and it's right where you'd expect it to be.
Now, when a path isn't continuous, we say it has a discontinuity, and limits help us describe these breaks. There's a removable one, which is just our simple hole in the path. Then you've got a jump discontinuity, where the path literally breaks and you have to jump up or down to get to the next piece. And finally, there's a vertical asymptote, which is like a cliff edge. The path just shoots up or down towards infinity as it gets closer.
And this all leads to one final really important rule. For a limit to exist at a point, the path coming from the left and the path coming from the right have to be heading to the exact same destination. If they're aiming for different heights, like with a jump, then there's no agreement, no single meeting point. So we just have to say the overall limit does not exist.
So, when you boil it all down, limits are this incredibly powerful magnifying glass. They let us analyze a function's behavior at its most interesting and sometimes broken points. And this one idea, understanding what happens near a point, is the foundation for finding the slope of a curve, which is the key that unlocks the rest of calculus. It really makes you wonder, doesn't it? What other secrets can this magnifying glass help us uncover?